All right, so this project for pre-calculus is the logistic model. Again, here are the instructions and the background information. And we'll jump right into the assignment. So part one, write and apply a logistic model for the data set. The U.S. Energy Information Administration collects data recording and the net generation of energy by wind annually and thousands of megawatt hours for each state. The graphs show the data for Kansas and California respectively. Some of the data points in these graphs are given in the table. Here's our table. Using the graphs, explain why a logistic model makes sense for this. Now, I know you're interpreting the data, and you might want to put this in a more complete sentence, but in both graphs, the data shows growth that appears to level out. The reason that the growth will level out is because there's a resource limit for generating wind in these states. When the growth is limited by resources, the best model is the logistic growth model, which recognizes that growth will not continue indefinitely. So up until this point, you've probably talked about exponential growth, which looks like this. And a logistic model is good when it starts to level out. So let's go back to the graphs. They start to level out here, and it's even easier to see in the California. At some point, it's going to level out. You run out of capacity for whatever the particular item is. So why does a logistic model make sense for the data? A logistic model is best. Logistics model is best because the data points level out. There you go. Referring to the data table, complete the following steps to create a logistic growth model in the form given for generation in the wind state, for wind in the state of Kansas. According to the table, what is the initial value of the data and how can this information be translated to an ordered pair? So the initial amount is the wind generated in 2001 for all sectors was 40,000 megawatts. Since x is 0 for the initial value, 0 represents 2001, which makes the initial point. And so we're going to turn that into an ordered pair, 0, 40. We don't want to include all these zeros because it becomes a whole lot of extra digits to carry around. So we're going to use the point 040. Letter B, based on the current resources, there's an estimated limit of 28,000 megawatt hours. How does this fit into the standard form of the logistic model? A is your limiting factor. A is 28,000, and I should have read this as 28,000 megawatt hours. So A is 28,000. Okay. C, using your answers from part A and B above, solve for the value B in the logistic function. So we have to say that Y is equal to A, 1 plus B, E to the negative RX. In this case, we know the initial amount is 40, so we'll say 40. And that A is 28,000 over 1 plus BE. Now, what's the X value? The X value is 0. But what's anything to the 0 power? It's just 1. So this is 40 is equal to 28,000 over 1 plus B. And when you turn around and solve that, B is equal to 699. If we keep going here, use the results from above and the data point for 2017 to find the value of R in the logistic function. So what we have to do here is say that Y is equal to 28,000 over 1 plus 699 e to the negative RX. So our job is to figure out what R is. Now, the data point for 2017, let's go back up. 2017 has these two values in it. So we're going to substitute those in for both the time and we're going to put them in for the Y value. So it will be, our Y value is 18,598 equals 28,000. 1 plus 699. E is E, negative R is what we're solving for. And then X is the amount of time. So 2017 is actually 16 years. It's 16 on our table. So the job is to solve for R. There's going to be some multiplying and some distributing that we have to do. And we'll do 18,598 times 1 plus 699 e to the negative 16r is equal to 28,000. So you can distribute and get all sorts of stuff. At some point, you're going to get e to the negative 16r is equal to 0.0007. And the way that you get rid of that e or move that on is to bring in a natural log. So natural log of e to the negative 16r is natural log of 0.0007. E and ln cancel out, so negative 16r is equal to ln of 0.0007. Divide both sides by negative 16, so r is equal to 0.4540. Based on your above calculations, write the logistic model for the data. So this is, again, where we just substitute everything in. So y is equal to 28,000, 1 plus 699 e to the negative 0.4540 x. Sometimes you see a t there. That's what I got a little confused about. And if you remember exponential growth equations, this is the exact same thing. The equation's just a little bit more complicated. Use the equation above to algebraically determine the estimated generated wind power in the year 2021 for Kansas. This table. So the first one is Kansas and the second one is California. Okay. So what we're going to do here is say that y is equal to 28,000 over 1 plus 699 e to the negative 0.4540. This time x is equal to 20 because the year 2021 would be 20 if time equals 0 at 2001. And when we use our calculator, we get 25,934,000 megawatts. Okay. Explain how you could use a graphing tool to verify that your answer to the above problem is correct. You could put it in the graphing tool and then trace along to where x equals 20 and look at the y value. I would recommend like Desmos is a really good website or an app. And you want to trace to x equals 20. And then just make sure it matches. Not 200, but 20. Good. Part 2, find and apply a logistic regression model. So what we need to do is use a graphing tool and the data provided in the table in part 1 to write a logistic regression equation for the generation of wind in the state of Kansas. What that means is you would have to plot the points, and I don't know how much practice you have with these. You'd have to plot the x's and the y's. This would be your 0, this is your 1, this is your 2. And that graphing tool, again, I recommend Desmos, will give you the equation. So the exact equation is y equals 28,856.2 over 1 plus, you know what I'm going to say as we're going through this? I'm going to say skip this. Because I guarantee you that the students in the building are not working on this, and I don't want you to do either. So this one's a skip. I won't mark it wrong when I look at your projects. This one's a skip. Number 3, in part 1, it was given that there's an estimated 28,000. Does this compare to your regression model? Let's do this one a skip. You could say that they're fairly close, but based on the regression model, yeah, this is a skip. This is too much for us. For part 3, justify and interpret your logistic models. Compare the model that you wrote part 1 with the one for part 2. Nope, we're going to skip these as well. I don't love this project. All right, so I appreciate your patience. We've now learned that going forward, I should just skip this whole project. But if you work on that part 1, then I'm a happy teacher. So don't worry about the rest of the logistic model. Just part 1. You do not have to complete parts 2 and 3. So sorry for the time that you might have tried on that.